And this is joint work with my advisor, Tim Roughgarden. So let's say that you want to estimate next year's GDP growth. You look at 3 economic models. One 3.5% growth, another 1.5%. A third expects the economy to shrink by 1%. You want to aggregate these into an all things considered best guess. This is the problem of forecast aggregation. So how might you do this? You could choose a random expert to trust. Or you could average all of the forecasts. Or if you have a prior, you could just ignore the forecasts entirely and go with the prior. Or you can do something more sophisticated. For example, you can take the average and then move that average away from the prior. This is called extremization, and it works well in practice. And to foreshadow our results a little bit, one of our main results will be a rigorous theoretical justification for extremization. I'll start by motivating and formulating our problem. And then I will give you our results in 2 different settings. First, the prior free setting, which is where the aggregator doesn't know the prior, and then in the known prior setting. So if we want to answer the question, which aggregation method should you use, we ought to have a framework for comparing different aggregation methods. And the perspective that we take is that we want our framework to look favorably on aggregation methods that work well in general across a broad range of possible setups. And so we will assess a method based on its expected performance in the worst case, that is, for an adversarially selected setup. To formalize what I mean, let me introduce information structures. So let's say that there are k experts, and we are interested in estimating a quantity y. So y could be next year's GDP growth or whatever. The experts start with a common prior over the states of the world. And then each expert receives a piece of private information, which we will call their signal, and update their beliefs based on their signal. Now, an information structure is just a joint probability distribution over all of the experts' signals and the outcome y. You can think of an information structure as describing the correlation between the experts' signals. As an example, you could have an information structure in which all of the experts' signals are drawn independently from a distribution D. Or you could have a different information structure in which all of the experts have the same draw from this distribution. Although the marginal distribution of each expert's signal is the same across these 2 information structures, these information structures are very different from each other because the joint distribution is very different. So here's our setting. First, expert signals, together with the value y that we're trying to estimate, are drawn according to an information structure. Then each expert computes the expected value of y conditioned on the signal that they received. And then they report this expectation as a forecast to the aggregator. The aggregator then uses an aggregation method to combine these reports into one aggregated forecast. And the aggregator is penalized based on the squared difference between their forecast and the true value of y. Now, our goal is to have a low expected penalty, a low expected squared distance, where the expectation is over draws from this information structure. And in particular, we want this expected penalty to be low for an adversarially chosen information structure. That's why this setting is known as robust aggregation. So how can we measure a method's performance on a particular information structure? So on the one hand, we definitely want to do better than someone who just knows the prior, ignores all of the experts' forecasts entirely, and just reports the prior. And by the way, even if the aggregator doesn't know the prior, they can easily do at least as well as this benchmark simply by choosing an arbitrary expert to defer to. On the other hand, the best that we can possibly hope for is that the aggregator does as well as someone who knows the entire information structure as well as every expert's signal. Now, doing this well is an unachievable utopia, but hopefully we can still compare we can still compare the aggregator against this benchmark. And so this suggests a natural measure for the performance of an aggregation method on an information structure, which is how far between this low benchmark and this high benchmark it scores. So formally, it is the aggregation method's improvement over the prior in terms of expected squared distance to the true value of y, divided by the improvement of an omniscient person over the prior. We call this the approximation ratio, and we're hoping to get it as far away from 0 and as close to 1 as we can. Now, I just want to say that really the approximation ratio is a means to the end of figuring out which aggregation methods work well across a broad range of information structures and in which settings. Now, you might start by asking, is there any aggregation method that consistently beats an approximation ratio of 0 for every information structure? Unfortunately, the answer is no, as demonstrated by the following example. In this information structure, two experts each receive independent random bits. And the value y that we are interested in is the XOR of these bits. Now, consider a particular expert. From their perspective, no matter which bit they receive, there's a 50% chance that y is 0 and a 50% chance that y is 1, which means that they will always report 0.5. This means that the aggregator doesn't actually receive any useful information from the experts and can't do anything better than just reporting the prior. Now, the intuitive thing that went wrong with the XOR example is that there were complementarities between the experts' information. That is, any one expert's signal was completely useless, but having both of them told you everything you need to know. And so a potential fix that you can try is to insist that your information structure has signals that have diminishing marginal value. So formally, in general, let A be a subset of the k experts. And we are going to let y sub A denote the estimate that would be given by all of the experts in A if they got together and pooled all of their signals. And the quality of YA is just the improvement of this estimate YA over the prior, again, in terms of expected squared distance. And so we could insist that our information structure satisfy the property that this quality function is a submodular set function. This is known in the literature as the weak informational substitutes condition. And so it's natural to ask, if you insist that your information structures have the weak substitutes condition, does that allow you to get a better than 0 approximation ratio? The answer is yes. It's a pretty straightforward consequence of the definition that simply choosing a uniformly random expert to trust gets you an approximation ratio of 1 over k, where, again, k is the number of experts. And unfortunately, you can't do better than that. While I won't go through the construction, there's an information structure that we designed that took advantage of a notion from cryptography known as secret sharing that demonstrates that no aggregation method can do better than the 1 over k guarantee that you get from choosing a random expert. So here's the story so far. Without any restrictions on the information structure, the best approximation ratio you can hope for is 0. If you insist on weak substitutes, then the trivial strategy of choosing a random expert gets you a 1 over k approximation. And doing better is impossible. And so the natural next question is, can we strengthen the weak substitutes condition to allow us to get better results? The answer is yes, and we call this notion projective substitutes. While I have the definition of projective substitutes on this slide, what I really want to take away, you to take away is the intuition for this definition. So weak substitutes, if you recall, is a condition on how well a pool of experts can do at predicting the value of y. Projective substitutes is a little broader. It considers how well a pool of experts can do at predicting what a different pool of experts believes. And so it turns out that this particular condition is a strengthening of weak substitutes. And basically, it captures the spirit of diminishing marginal returns in a broader context. So does projective substitutes let you do better? The answer is yes. In particular, by averaging all of the experts' forecasts, you can get a 1.9 over k approximation guarantee. This is a significant improvement over the 1 over k bound for weak substitutes. But perhaps more importantly, under the projective substitutes condition, we have a formal separation between how well we can do by choosing a random expert versus the more sophisticated strategy of taking the average of all of the experts. So I won't go through the proof of this fact, but I will give you the main idea. So it turns out that under projective substitutes, one of two things must be true. Either the experts' forecasts are somewhat accurate on average, or the experts' forecasts are fairly different from each other. If the experts are somewhat accurate, then we're done. We can choose a random expert to trust, or even better, you can average all the experts. If the experts' forecasts are fairly different from each other, then averaging all of the experts' forecasts allows you to do substantially better than just taking a random forecast. And remember that taking a random forecast gets you 1 over k, so this is substantially better than that. So that's how we get this 1.9 over k approximation guarantee. Can we do better than that? Well, maybe, but certainly not by much. In particular, we have a negative result that I won't go through, but it shows that no aggregation method can beat an approximation ratio of roughly 2 over k, even under the projective substitutes condition. So here's a summary of what we know so far. The line that you see in gray here, that is the guarantee that you get from weak substitutes, where the x-axis is the number of experts. There's a substantial improvement between that and what you get by averaging the experts under projective substitutes. And then there's a small gap between that and the negative result we have, which is how well you could possibly hope to do right now under projective substitutes. So far, we have been assuming that the aggregator does not have access to the prior. That is the expected value of y unconditioned on any other information. And our 2 over k negative result, in fact, relies very heavily on this. If the aggregator knew the prior, they could, in fact, pin down the exact value of y in our bad example. And so it's natural to ask, OK, if we allow the aggregator to use the prior, does that allow them to do better? And the intuition for why you might hope that it allows them to do better is that it's important for the aggregator to know not just the experts' forecasts themselves, but also the direction in which the experts updated away from the prior. In particular, if the expert knows this, then a sensible thing for them to do is to take the average of all of the experts and then shift that average away from the prior. This is known as extremization. Now, this might be unintuitive, so I'm going to give you a few motivations for extremization. First, consider a coin with a uniformly random bias between 0 and 1. And we're trying to estimate the bias of the coin. Each of 2 experts flips the coin. And it turns out, if you do the math, that if an expert sees heads, the right thing for them to report is 2/3. So let's say both experts see heads and report 2/3. Then ideally, the aggregator would consider that there are 2 coins that came up heads and say something even higher, specifically 3/4, which is extremizing the average of the expert's forecasts away from the prior of 1/2. Intuitively, what's going on here is that each expert mixes the evidence that they get with their prior. But if you want to aggregate, then you don't want to count the prior once for each expert. You just want to count the prior once. And so extremizing is essentially a way to counteract the fact that the average counts the prior multiple times. Third, it turns out that empirically extremization works very well, much better than averaging without extremizing. Now, if you wanted to extremize, the simplest thing that you might think to do is to pick a particular constant d, and to move, and let's say d is greater than 1, and to move the average of the forecasts away from the prior by a factor of d. This is called linear extremization. So you might ask, under projective substitutes, is there a choice of d that allows us to do better than what we could do in the prior free setting? The answer is yes. In particular, for a choice of d that's between 1 and 2, growing with k up to an asymptotic value of the square root of 3, you can get a roughly 2.6 over k approximation, which is a big improvement, not just over the 1.9 over k positive result that we got, but in fact over the 2 over k negative result. That is, you can do better if you know the prior than you could have hoped to do in the prior free setting, simply by applying linear extremization. So here the black line shows what you can get for projective substitutes by linearly extremizing. So I'm going to end with a bit of speculation. As it turns out, linear extremization, maybe it does better than this 2.6 over k that we proved, but certainly not more. In particular, we showed that you don't do better than 4 over k. Maybe there are more sophisticated ways to extremize. One idea that we had was to use the variance of the experts' reports. The intuition for this is that if the experts' reports are really similar to each other, then they're probably based on similar evidence, which means that you don't want to discount the prior too much when aggregating, and so you don't want to extremize very much. On the other hand, if the experts are very different from each other, then you might want to extremize a lot. So I see this as an exciting and potentially fruitful direction for improving our results. I am going to leave this slide with some potential other directions for future work up on the screen as I take questions. Thank you.
Time for questions? Okay, real quick, we've got one online from Jason Hartline. Why are the experts reporting their posteriors and not their signals? You might have answered that already.
So the answer is that signals only mean something if you know the information structure. Right? The signal is just, it doesn't have to be a number. Like, it's just some sort of arbitrary designation of like what each expert knows about the state of the world. And so if the aggregator doesn't know anything about the information structure, then there isn't really a clean way to report more than just the expectation.
It's actually related, but well, we can ask them to report more than just the expectation, maybe the whole distribution or some more information. Would that help?
That's fair, yeah. I guess that you can report more than just the expectation, and I think that that is an interesting direction for future work.
Do you exist settings where you get something from these current definitions of performance that doesn't scale down to k? Because it seems like each time we're getting better at constants, but we still have linear scale.
That's a good question. It is an open question in my mind whether in the known prior setting you can do something fancy and get something that grows asymptotically better than 1 over k. I think that's very plausible.
You have mentioned that the extremization essentially it works in some way to not count the prior multiple times. But you have already mentioned that when the evidences are agree with each other, we may do it better by extreming by a little less. So I feel that maybe, I have no idea, but maybe the extremization is kind of ad hoc. And I just imagine, is there a better way to more cleanly not overcounting the prior too much?
Maybe. The challenge you face is that all you know is each expert's expected value conditioned on their signal. If you knew stuff about the information structure, I think you could do something more sophisticated, but you're sort of pretty limited by the fact that you only have this very sparse amount of information about what's going on.